Okay, thanks Chris, and thanks Ted, and thank you to everyone joining us today. So as Chris mentioned, our objective today is to look at the various strategies that are available to accelerate database performance with different uses of memory. A number of alternatives exist to improve the performance of database-intensive applications, and some of these alternatives didn't exist until relatively recently. One alternative is to create a RAM disk and run the database out of that RAM disk. Another alternative is to configure your database management system to allocate a large enough cache to hold the entire database. Yet another option that some database systems offer is to create memory tables. And one of the most recent options is to use solid-state disk drives, which are essentially NAND flash memory. On the surface, it might seem that these options would deliver performance that would be comparable to in-memory databases, such as Times10, Polyhedra, and our own ExtremeDB. And it's certainly true that these techniques will improve the performance of database management operations, but they're not equivalent to true in-memory database systems, and they have some other disadvantages that we'll discuss in today's presentation. The RAM disk, cache, and solid-state disk alternatives are all based on the assumption that a file system is present. A RAM disk is a file system that's created over a region of DRAM, the size of which is sometimes configured in the operating system startup sequence, but some RAM disk drives allow the RAM disk to grow in size on demand, and they can eventually exhaust all the available system memory. The cache employed by conventional database systems is a technique to keep frequently accessed data and index pages from the database files in memory for faster access. If a needed page is already in the cache, then a file I/O operation is avoided. Solid-state disks are similar to RAM disks, except that they're a block device with a device driver that the operating system sees much the same as a hard disk drive. So for example, a solid-state disk can be used as a boot device, whereas a RAM disk can't. Also, solid-state disks use NAND flash memory, not RAM, so not quite as fast. Because attempting to improve database performance by these three alternatives, in other words, the RAM disk, cache, and solid-state disks, all assume that there's a file system, we need to understand how database systems interact with file systems and the optimization strategies that are hardwired into database runtime based on those interactions. The average seek time of a hard disk is about 9 milliseconds. Compare that figure to 60 nanosecond RAM or 1 or 2 gigahertz CPU clock cycles, and it becomes very apparent that file I/O is extremely expensive in terms of performance. So improvements that database system developers can make in that area, in the area of avoiding file I/O, is going to outstrip improvements in any other area by a very wide margin. So not surprisingly, minimizing file I/O is the major focus of optimization for conventional database systems. In fact, executing CPU instructions and accessing RAM are so much faster than file I/O that it's a very reasonable trade-off to use more CPU cycles and use more RAM if doing that helps you avoid file I/O. And the major way by which database systems avoid file I/O is by creating and maintaining a cache. And this involves exactly the trade-offs that I just described. The cache uses memory, and the logic to create and use the cache uses CPU cycles. So we're using memory and we're using CPU cycles to avoid doing file I/O. Databases written with the assumption that a hard disk drive is the storage medium also tend to assume that storage space is relatively abundant and that the time to write 100 bytes is not meaningfully different than the time that it takes to write 10 bytes. Therefore, it's also a reasonable trade-off to use extra storage space if doing that will also help you save file I/O. The database runtime doesn't know when you create a conventional database in a file system that's in a RAM disk or on a solid-state disk. A file system is a file system as far as the database is concerned. The database runtime is going to create the cache regardless. Depending on the database vendor, the database runtime probably gives you control over the size of the cache so that you can make it as small as possible, but you can't eliminate it because the database runtime has all that logic baked into it. In fact, as we'll see in a couple of slides, you might not even want to minimize the size of the cache, even if the database is in a RAM drive. In contrast, in-memory database systems do know that there's no file system involved, and therefore there's no file I/O to avoid. So the major objective of conventional database system optimization, that being avoiding file I/O, is removed from the equation. In its place, the major objective becomes minimizing memory consumption. The limiting factor is no longer disk performance and becomes the amount of data that can be under management. RAM is generally not as abundant as spinning memory. A secondary goal of an in-memory database is, or at least it should be, minimizing the CPU cycles used by the database runtime. After all, the primary objective of putting a database in memory by any means is to improve the performance, right? So we want to minimize CPU cycles to improve the performance further. By creating an in-memory database system, we've eliminated the biggest impediment to performance, that being file I/O. So the next logical step is to reduce the code path, in other words, the number of CPU cycles. The net effect of the primary optimization objective of conventional databases is that they use CPU, memory, and storage space less efficiently than an in-memory database. Remember, we've established that trading CPU cycles, memory consumption, and efficient use of the storage space to minimize file I/O is a good trade-off. In the next few slides, we'll look at exactly what attributes of conventional database systems play a role in this less efficient use of CPU and memory, specifically indexes and the cache. Just about everybody studied B-tree indexes in computer science class. B-trees are organized as an upside-down tree with the root node at the top, then internodes, and then leaf nodes. Database systems normally conduct their input and output operations in terms of database pages. So instead of reading just a few bytes to satisfy a given read request, an entire page is read or written as the case may be. So the database runtime is going to read and write entire nodes of the tree at once because a B-tree node equates to a database page. Database pages, or B-tree nodes in this case, are in turn usually a multiple of the disk blocking factor, so typically 4K or 8K bytes, for example. And that creates an extra little bit of efficiency because disks always read and write entire blocks, regardless of how much I/O you request of them. So it wouldn't make sense to create a database page of, say, 1K bytes, knowing that the disk is going to read 4K bytes regardless and then throw away 3K. That would just be inefficient. So we always map our on-disk database pages to the blocking factor of the storage medium. Now, each of these B-tree nodes is organized as a number of fixed-length key slots. The number of slots per page is a function of how large the key values are. In other words, is this an index over a 4-byte integer or over a 20-byte character array? And also the size of the page or the node and the amount of overhead that the database vendor's index algorithm imposes for metadata, such as pointers to a subtree, the database address, or the row ID of the associated table row for that given index entry, and so on. The metadata could be in the range of 10 to 16 bytes per slot, and then some additional metadata in each page header. The indexed data, in other words, the key values, are stored in the key slot. This is one of those optimization strategies to minimize file I/O. Remember that we established that storage space is cheap and abundant, and that it costs relatively little or a little more to read or write 100 bytes versus 10 bytes. So using extra storage space is a reasonable trade-off if it can reduce or eliminate file I/O later on. And that's exactly the case here. If a query can be resolved with just a key scan, then we save one I/O compared to having to access a key slot, extract the row ID, seek to that row's location, and then perform another I/O to read that row data. So for example, a query such as select title from book order by title in order to populate a pull-down combo box in a form can be satisfied with just a key scan. By using the more storage space to store the key value in the B-tree node slot itself, the database has reduced file I/O by about 50%. So that's a good trade-off. We're using extra storage space to reduce our file I/O by about half. But now also recall from your computer science courses that a B-tree is by definition always balanced, and that the byproduct of a balanced tree is that on average about 45% of the node space is empty or unoccupied. So when that B-tree node is in memory, which would be the case if you're caching your entire database or you're putting it into a RAM drive, then almost half of the memory that's used for the node is effectively wasted. It's empty space. So in other words, the technique that uses extra storage to avoid file I/O doesn't use memory efficiently when the page is in cache. Now, an in-memory database wouldn't benefit from saving 50% of the file I/O by keeping the key values in the slot. There isn't any file I/O to save. So we organized the tree differently. First of all, RAM isn't a block device, so there's no particular advantage to creating a page size that's a multiple of a disk blocking factor, or for that matter, even making the page size a multiple of 2. It's just human nature to like those kind of round numbers. So in my example here, the page size can be 256 or 512 bytes. Next, since we're not keeping the key values in the slots, there's one more reason not to have a large page size or B-tree node size. Without the key values in the key slots, we can pack as many slots into a smaller page size. Also, when the B-tree search algorithm determines which node of the tree contains the search value, it reverts to a binary search of the slots in that node to find the specific slot that has the search value. So a balance needs to be struck between the number of slots per node, which affects the depth of the tree, and the time required to finish the search with the binary search within the node. So we don't want the tree to be too deep, but we also don't want our nodes to have so many slots that that binary search within that node consumes too much time. So we need to find that balance. Being in memory doesn't change the fundamental algorithm of B-trees, so there's still going to be 45% empty slots. But the slots are smaller, and therefore the whole tree is smaller. So even though the percent of wasted space is the same, the absolute amount of wasted space is less. In other words, 45% of 100K is less than 45% of 500K. So the amount of storage space required for a B-tree in an in-memory database is a fraction of the storage space required for a B-tree in a conventional database, which becomes really important when that conventional database is being created in a RAM drive or you're wanting to cache 100% of the database in memory. In other words, the amount of memory that you need will be far, far greater than if you'd have just created the database in a true in-memory database in the first place that uses the memory more efficiently. Let's go a little bit further with the analysis of the benefit to caching 100% of the database in memory. A cache can only improve read performance. In order to preserve the ACID properties of transactions, a conventional database system has to write all the updates through the cache and record them on the physical media. During a transaction, the database will attempt to keep all the changed pages, or what we call dirty pages, in the cache. But when the transaction is committed, those changes have to be recorded in a durable fashion. Now, the details are going to vary from one database system to another, but file I/O is always going to be involved. As I mentioned previously, the pages in cache are a mirror image of the pages that are stored on the file system, including all of the unused space on those pages and the redundant data in the indexes. Even though when the database is 100% cached, and you can guarantee that the data rows associated with every key slot are in memory, and therefore they're fast to access, the database system wasn't built with that knowledge, and it's still going to build that redundant data into the key slots and waste that memory. Most database systems don't have any explicit means to preload the database into cache. In practice, that means that you're going to have to read every row of every table and scan every key to cause all of those database pages to be loaded into the cache. And it isn't enough to scan just one key of a table and use it to cause the associated data pages to be loaded into cache. You need to scan every key to cause all the index pages to also be loaded into cache. Now, ExtremeDB Fusion, which is our hybrid in-memory and on-disk database system, is an exception to that statement. We do have a pair of functions to save the cache to a file prior to shutdown and to load the cache from a previously saved image, which can be useful in some contexts if you want to start with a hot cache. But we didn't really create that capability for this caching the entire database purpose. ExtremeDB is already an in-memory database, so that need didn't really exist. It's also important to note that loading up the cache is only useful if the database cache is actually shared. Now, that would be the case for most client-server database systems, but it's not always the case for embedded databases. With embedded databases, each application includes the database runtime code within its own address space. In other words, the database runtime functionality is embedded into the application, which is where the term embedded database comes from. In that scenario, each application may also have its own database cache, its own private cache, and we call that a distributed cache architecture. And the pages in that cache can only be guaranteed to be in sync with the physical database when that application is holding locks and preventing other processes from changing the physical database pages that it has a copy of in its cache. As soon as those locks are relinquished, that guarantee is void, and so those cache pages get invalidated, meaning that the next time that application wants to access those pages, they have to be reloaded from the database the next time the application acquires locks. So with the distributed cache architecture, it simply isn't possible to employ this approach of caching the entire database. And then finally, the logic to create and maintain the cache is complex. Let's look at just the subset of code that deals with determining whether a requested piece of data is in the cache or not. When a read request is submitted to the database engine, it has to consult an index in the database runtime's data structures to determine if the page in question is already in the cache. If it's not in the cache, and if the cache is already full, then a page to remove from the cache has to be nominated. That's usually an implementation of a least recently used, or LRU, algorithm. If the page selected to be removed from the cache is dirty, in other words, it's been updated during the transaction, then it has to be written somewhere in a manner that will preserve the integrity of the ACID properties. It either has to be written in a staging area outside of the database, or it has to be written to the database with enough additional information to be able to undo that write to restore the original page in case the transaction is aborted or the process terminates unexpectedly before the transaction is committed. The flowchart shown here and that I just described is actually very simplified. There's additional logic to deal with cache coherency and cache synchronization in multi-user, multi-process, and multi-threaded environments. All this logic uses CPU cycles. Again, for a conventional database with some subset of the pages in cache, that makes a lot of sense. We can do a lot of processing with the CPU in a fraction of the time that it takes to do a single 9-millisecond disk I/O. But when the database is going to be 100% in memory, which is the case when we decide to create a RAM disk or a cache large enough for the entire database, that trade-off of CPU cycles to avoid disk I/O no longer makes sense. Now, earlier I mentioned that you might not want to minimize the size of the cache even if the database is created in a RAM drive. And this cache lookup logic that I just described is the reason why. As you can see in the flowchart, a number of other decisions are made if the page isn't in the cache. Remember, the database system doesn't know it's in a RAM drive. All the database system knows is that's a file system. So to the database system, as I said, it's just another file system. So if you reduce the cache size to the minimum, you'll force the database system to thrash or constantly swap pages in and out of that tiny cache that you've allowed, and the full extent of the logic outlined here is going to execute over and over again. So on the flowchart here, that second question, is the cache full? If you've created a tiny cache, the answer is always going to be yes. So it's going to branch down the more extensive side of this logic, and it's going to execute the full extent of that logic over and over and over again. So even if you're putting the database into a RAM drive, you might not want to create a super small cache. Whether a database is in a RAM drive or a solid-state disk, or you've cached the entire database, there's a lot of steps involved in moving a piece of data across the boundaries, as I've shown on this slide. In fact, this slide simplifies the case because most database systems have some sort of transaction logging mechanism to support the ability to roll back or abort a transaction or to perform roll-forward recovery after a system failure, or both, and that's not depicted at all on this slide. So for every arrow on this diagram, there should be a corresponding arrow in the opposite direction to represent inserts, updates, and deletes. And in that case, there would be another set of arrows and boxes to represent the transaction log file in the file system cache as well as on the file system's physical media. So it should be obvious that all the movement of the data takes time and it has its associated impact on performance, even when all these locations are represented by locations in memory. In contrast, a true in-memory database normally has just two copies of the data that move between the database and the application to the database management system. Now that we know how the optimization strategies affect data and index layout, database management system logic, and trade-offs between CPU, memory, and storage space, we can summarize the benefits and drawbacks to the various options that are available to us for accelerating database applications. Let's start with just using our database system's ability to create an arbitrarily large cache. Every database product I can think of would permit you to create a cache large enough for the entire database, provided that you have enough RAM available to do that. Having 100% of the database cached is certainly going to improve performance, and it's pretty easy to implement. You're just using the facilities that are already available to you in the database management system. But because on-disk databases are wasteful of storage space, it could take anywhere from 20 to 100 megabytes to store just 10 megabytes worth of raw data. In other words, anywhere from 100% to 1,000% overhead. So for any moderately large set of data to store in a database, you simply might not have enough available memory to cache it all. And the cache, as I explained earlier, doesn't improve write performance, it only improves read performance. And finally, the cache logic is going to be a drag on performance. On every page access, that code to determine whether the page is in cache or not has to be executed, and during writes, pages have to move across all the boundaries that we showed on the previous slide. The major limitation of caching 100% of your database is that it doesn't address the performance of inserts, updates, and deletes. To improve those operations, we could create a RAM drive and store the database in the RAM drive. RAM is orders of magnitude faster than a disk, so our update performance is also going to be vastly improved. But that begs the question, is that going to be as fast as an in-memory database? So we ran a test to quantify the difference between an in-memory database system and a conventional database system with the database in a RAM drive. The test was executed with Red Hat Linux with a 400 megahertz Intel Celeron processor and 128 megabytes of RAM, which is a modest system that was chosen for its similarity with the resource-constrained environments of many embedded systems, which are the primary focus of this webinar. And as you can see, the performance difference was dramatic. The in-memory database reads were 45 times faster, and writes were 100 times faster, which can be attributed to the considerations that are presented today: the unnecessary cache logic, the artifacts of transaction logging, and the overhead of the file system itself. Further, the in-memory database's emphasis on conserving memory resulted in a database size of 20.85 megabytes when fully loaded with the data. Now, the raw data size was 16.7 megabytes. Compared to the RAM disk database size, which came out to be 31.8 megabytes, or approximately 50% larger than the true in-memory database size. Incidentally, that same equation would apply to creating a cache large enough for the entire database. Whereas the in-memory database needed under 21 megabytes of memory, we would have needed almost 32 megabytes of memory to create a cache large enough for the entire database. So a RAM drive is relatively easy to set up and probably comparably easy to creating a cache large enough for our database, and it gives us the added advantage of also improving the performance of insert, update, and deletes. And a RAM drive is transparent to the database system. It's just another file system, so you're going to use the database system in the same way that you always would. But we're going to need a lot more memory for a RAM drive than we need for the same database if we were using a true in-memory database system, and we would also need more for the RAM drive than we would need for the 100% cached approach, because the file system is going to impose its own overhead for metadata such as inode tables, free block bitmaps, and so on. And depending on the RAM drive implementation, it could exhaust the available memory, which is first going to cause our system to slow down and ultimately crash. So for example, there's two prominent RAM drives for Linux, RAMFS and TempFS. RAMFS will allow the file system to grow unchecked until there's no more memory, while TempFS has a size limit imposed on it when it's created. Because the RAM drive is transparent to it, the database management system is still going to go through its usual cache logic, and because the cache won't be equal to the size of the database, there's going to be more interaction with the RAM drive file system to swap pages in and out of the small cache. So query performance should be somewhat lower than the 100% cached solution, but our write performance is going to substantially outperform the fully cached database solution. Everything that I've talked about up to this point applies equally to solid-state drive technology. Again, the database system just views the solid-state disk as yet another block device with a file system. So the same optimization strategies, cache logic, additional moves and copies of the data, and so on still apply. NAND flash device prices are dropping, and the capacity has increased dramatically. which has in turn led to the increasing prevalence of solid-state disks in the data center and in netbooks and notebooks, for example. However, it's also the case that NAND flash memory quality has been dropping. The 90 nanometer generation of NAND technology in 2004 offered 100,000 rewrites of memory cells and data retention of about 10 years. The current 30 nanometer 2-bit per cell technology supports write cycles of only about 3,000 and data retention of just about 1 year. And then the 3-bit per cell chips that are emerging have only a few hundred write cycles. But that decline in quality is offset by the increase in capacity. In other words, I may have 90% fewer write cycles, but instead of 128 megabytes of capacity, I have 2 gigabytes of capacity, and for a lower cost. As this graph illustrates, NAND flash memory is still more expensive than hard disks, but when power consumption and heat generation within data centers is factored in, they're beginning to make economic sense when compared to 2.5-inch hard disk technology, and the prices, of course, are forecasted to keep dropping over the next few years, such that wide-scale use of NAND flash memory in place of hard disks is economically feasible. And lastly, on the use of solid-state disks with conventional databases as an alternative to in-memory databases, consider the speed differential. The solid-state disk will certainly speed up database applications relative to a hard disk. The transfer rates are comparable, without getting carried away about digging into serial ATA, SCSI, RAID, and other technologies. But the access time of solid-state drives is vastly superior, typically 200 or 300 microseconds, compared to 9,000 microseconds for a hard disk. But even solid-state drive performance pales next to RAM. Double data rate synchronous dynamic RAM, or DDR SDRAM, has transfer rates of at least 1,600 megabytes per second and up to twice of that, and access times varying from 7 to 70 nanoseconds. When you combine the superior performance of DRAM with the optimization objectives of in-memory databases, and compare that to the performance of solid-state drive technology compared with the optimization objectives of conventional databases, then you easily conclude that in-memory databases will outperform conventional databases on a solid-state drive by a wide margin. So like a RAM drive, solid-state disks are transparent to the database system. You'll just use the database system like you always have. The solid-state disk is going to improve read and write performance relative to a hard disk. And there are power and heat advantages that might be important in battery-powered devices and in data centers. On the other side of the ledger, NAND flash has relatively short life expectancy. This is compounded by the fact that database management systems perform a lot of writes to enforce the ACID properties, keep indexes balanced, support database recovery, and so on. So database systems tend to be hard on flash devices. And while they're faster than a hard drive, solid-state disks are not as fast as RAM, but you get persistence for free, so to speak, which can't be said of the RAM drive solution. Before moving on to talk about memory tables, let's summarize what we covered regarding RAM disks, solid-state disks, cache, and in-memory databases. An on-disk database doesn't change its fundamental nature if you put it into a RAM disk. It still creates and maintains a cache, which is a waste of memory and CPU cycles when the database is already in RAM. Caching an entire database is much better. You haven't eliminated the cache, obviously, so the database system will still use those cache-related CPU cycles, and the cache can only improve read and not write performance. Solid-state drives improve write performance as well as read performance, but a solid-state drive is still not as fast as RAM, and today they're substantially more expensive than hard disk storage. The memory consumed either by a cache or storing the database in a RAM drive is vastly greater than a true in-memory database due to the optimization assumptions and the strategies and the file system overhead in the case of the RAM drive solution. So we can conclude that the memory consumption is excessive and that the performance suffers due to the cache logic, the additional numbers of times that data has to be moved from place to place, and the CPU and system resources needed for the copies and the movement of the data, and in the case of the RAM drive, the file system overhead. So the bottom line is, if a solid-state disk delivers enough performance and it's not cost prohibitive, and the requirement to replace worn-out devices more frequently is acceptable, then it's probably a better solution than either caching your entire database or using a RAM drive. But if you need the performance that only RAM can deliver, then forget about the RAM drive and the caching options and use an in-memory database. You'll have a more streamlined solution that's working in the way that it was intended to work and using the CPU and available memory far more efficiently. There isn't time to cover it today, but there are also many options available to you for providing persistence to an in-memory database, so you can have the performance advantage without putting the database at risk in case of power loss. In fact, we have a white paper on our website that talks about this, and maybe Ted can dig up the URL for that and paste it into the chat window. So after considering the options and determining that an in-memory database is needed for performance, there's a new set of options to consider. Some database systems offer a memory table feature, and other database vendors have added an in-memory option to their on-disk database products. Either option might mislead you to conclude that the in-memory database technology as a technology on its own is no longer relevant, but that's simply not true. In the first case, memory tables don't change the underlying assumptions of the database system engine and the optimizations that are incorporated into it that we've talked about today. For example, the way that B-tree index nodes and node slots are organized are just the same for indexes created for memory tables as they are for conventional disk tables. In other words, the database management system has one set of index creation, maintenance, and lookup functions, and those same functions are used regardless of whether the index is for a memory table or for a disk table. So the memory for an index on a memory table is going to waste just as much space as if you had created the fully cached database approach or put the database into a RAM drive. And they vary from vendor to vendor, but memory tables have more restrictions than conventional file tables. Now, in the second case, the so-called in-memory extensions to conventional databases, these implementations are in reality just using memory as a substitute for files in a file system, and again, the underlying assumptions of the database engine haven't changed. The only advantage to be gained here is eliminating the RAM drive. In other respects, these implementations are identical to storing a database in a RAM drive, just without the RAM drive. They're on-disk databases that happen to be operating in memory. That's not the same thing as being an in-memory database, and the difference can be seen in the performance and in the efficient use of memory. So let's look at two examples of memory tables and one example of in-memory extensions to what is fundamentally a disk-based database. In MySQL, memory tables must use fixed-length slots, so they can't contain blob or text columns. So that's a limitation on in-memory tables that doesn't exist for disk-based tables. Disk-based tables obviously can contain blob and text columns. The maximum table size for a memory table is 4 gigabytes, and the maximum key length is 500 bytes. The key length restriction tells you that the physical structure of B-tree index nodes is identical for memory tables as for file tables, because when the key values are not stored in the key slot, which would be the case for an in-memory database, they don't affect the width of the slot, and therefore they don't impose any artificial limits on the length of a key. With memory tables, space that is freed up by deleting rows in that memory table can only be used for new rows of that same memory table. In contrast, for an in-memory database, when something is deleted, that free space goes back into the general database memory pool and can be reused for any subsequent need, whether it's for a row of the same table, a row of a different table, for a transaction buffer, for a tree node, or anything else. And when you're using MySQL's replication, slaves won't know when a master ceases to exist and will keep the replicated memory tables. And on restart, the master process has to explicitly recreate the memory tables or take some other explicit action to reinstate the consistency between the master and the slave database for those memory tables. So with respect to memory tables, the notion of database replication, keeping the master and the replicas synchronized, is broken in that circumstance. With SQLite, memory tables can't be shared, which really relegates their usefulness to user-defined temporary tables. Also, an entire database, not just certain tables, has to be in memory. But as a technique to gain greater concurrency, since SQLite does database locking, not table locking or row locking, but database locking, SQLite allows applications to open and attach to more than one database and to have transactions that span database boundaries. However, If the main database, the first database, is an in-memory database, then SQLite no longer enforces the ACID properties of transactions. So if you're going to have one in-memory database and one or more on-disk database, make sure that on-disk database is the first database. Otherwise, you risk compromising the integrity of your databases. Now, in-memory databases can't be saved to persistent storage with SQLite, although you can find one or more third-party patches that will supplement SQLite with this capability, but it's not part of the core SQLite capability. So it's apparent from the limitations of memory tables that they were really added as an afterthought, and therefore they don't have the same design criteria as a true in-memory database system would. And the constraints imposed on the memory tables also indicate that really their intended use was more as temporary tables, for example, to support fast lookup of coded values. And in some cases, the integration of memory tables and file tables is incomplete, leading to circumstances in which the integrity of the database can be compromised by their use. In contrast, a true in-memory database system regards the integrity of the entire database, or databases as the case may be, as a fundamental covenant between it and the database user. BerkeleyDB is probably the best known of the class of on-disk database products that purport to offer in-memory database capability. But a quick examination of the in-memory database requirements for BerkeleyDB reveals that, in addition to some pretty serious limitations, it's really just a means to substitute RAM for file storage, and that all the other assumptions about how to build and maintain the database are unchanged, such as the cache, indexes, and so on. I've extracted a few passages from the BerkeleyDB documentation to illustrate my point. The first statement tells us right off that the in-memory capability of BerkeleyDB is really just a modification of alternative number 2, which was creating a cache large enough to hold 100% of your database. On-disk database systems invariably use transaction log files to either provide the ability to roll back an aborted transaction or to perform roll-forward recovery after a crash. The entire notion of a transaction log is a byproduct of how on-disk databases operate. That the notion persists even in the context of presenting the database product as an in-memory database reveals that it is not, in fact, an in-memory database by nature. This is revealed further by restrictive limitations such as the inability to support more than one process. There's no reason that an in-memory database shouldn't be able to support multiple processes. And that extra 25% that BerkeleyDB imposes for overhead is also evidence that the assumptions and the optimizations embedded into the database runtime are geared towards on-disk databases and the additional overhead they impose to minimize file I/O. And the last point with respect to BerkeleyDB that highlights the fact that support for in-memory databases is incomplete is the limit on the maximum size of a transaction. When the transaction buffer is a disk file, there's no practical limit to the size of a transaction. Disk space is abundant. But there's no inherent reason that the maximum size of a transaction in an in-memory database should be predefined. But since BerkeleyDB's implementation of an in-memory database is just memory analogs for file-based artifacts like transaction logs and buffers, limitations like this have to be imposed. So, summing up here, these limitations point out that memory tables were an afterthought, and constraints on memory tables also indicate that their intended use is more as user-controlled temporary tables, not as a substitute for an in-memory database. And in some cases, these memory tables are not completely integrated with the rest of the database system. And then the so-called in-memory extensions to database systems that were originally on disk suffer from wrong-way optimization goals and invalid assumptions that stem from the original developer's assumption that the database was going to be on disk. Consequently, the performance is only going to be marginally better than a database in a RAM drive by virtue of eliminating only the file system. All the artifacts of an on-disk database system are still going to be present, the cache, the transaction logging, and so on. But I want to make clear that my purpose in this last section hasn't been to disparage MySQL, SQLite, or BerkeleyDB. Instead, my purpose goes back to the title of the presentation, what makes a database system in memory, and to distinguish a true in-memory database system from other technologies. MySQL, SQLite, and BerkeleyDB are fine products, and each have their own set of advantages that might make them the best choice for certain use cases. But if you've concluded that you require an in-memory database, then seek out an in-memory database system, one that was originally written with the intent of being an in-memory database system. For that use case, anything else is going to be substandard. So with that, I'm going to hand it back over to Ted to moderate our question and answer session.
Thank you, Steve. And as mentioned, you can submit questions for us now. You can use the Q&A box on the lower right side of the screen. And one question that's come in is, with an in-memory database, if the system goes down, isn't all the data lost? And doesn't this risk of loss offset any performance gains provided by the IMDS compared to caching and solid-state drives?
Well, whether or not that risk of loss offsets any gains is really a subjective thing that I can't answer for you. With respect to the first half of the question, the answer really is it depends. If you've created a pure in-memory database and you've done nothing else to provide persistence for that in-memory database when either the application closes or the system loses power unexpectedly, then yes, you're going to lose that data. And as I mentioned early in the slide, there are steps that you can take to provide persistence for an in-memory database. You can put the database into battery-backed RAM. You can incorporate transaction logging, which times 10 does by default, but you have to explicitly do that with ExtremeDB, for example. You can use a high availability version so that you maintain two copies of the database, a master copy on one system and a standby copy on another system, with failover to the standby in case the master fails for any reason. Or you can use, in the case of ExtremeDB, we have a ExtremeDB cluster, which is similar to high availability, except that with cluster, every database instance in the cluster is both readable and writable. With high availability, only the master is writable. The replicas are all readable but not writable. So there are a number of options available to provide persistence for in-memory databases.
Any additional questions from the audience? Here's one that's come in. Doesn't using non-volatile RAM for DBMS deployment provide the same benefits as using a solid-state drive?
Non-volatile RAM meaning battery-backed RAM or flash? Because those non-volatile RAM is a term that's used to refer to both battery-backed RAM and flash devices.
That's not specified.
Okay, well then let me assume that they meant flash, and as I explained in the presentation, flash or solid-state disks, whichever the case may be, are certainly faster than hard disks, but not as fast as RAM. Typical access time for a solid-state disk is 200 to 300 microseconds. That's still substantially slower than RAM, so you're not going to get the same benefit by using that type of non-volatile RAM. If the questioner meant non-volatile RAM in the sense of battery-backed RAM, then yes, absolutely, you get persistence and you get the performance that you would get and expect of an in-memory database, because that form of non-volatile RAM is just RAM.
Any additional questions? What are the size limits of an in-memory database?
Well, it's really the amount of physical RAM that you have available in your system. You could create an in-memory database that's larger than physical memory on a virtual memory system like Windows or Linux, but it isn't a good idea, because as you fill that database up, you're going to force the operating system to swap those in-memory database memory pages in and out of the swap file, and that performance is going to be worse than if you had just put the database into a disk-based database and created a cache as large as you could, because the database is going to more intelligently manage that cache than the file system will. The file system doesn't know anything about the database. The database does, of course, know about the database.
Another question that's come in is there support, presumably in ExtremeDB, for serial flash memory?
I'm going to have to get back to the questioner on that one.
All right. And another question that's come in is, what kinds of applications use an in-memory database?
Oh, wow. There's a wide variety of applications that use in-memory databases. The rationale for using an in-memory database can be that you need the performance that you can only get from an in-memory database. So a lot of high-performance computing type applications in the capital markets, high-frequency trading, algorithmic trading, risk management, and so on. From the world of embedded systems, there's a whole bevy of devices out there that simply don't have any persistent storage, and yet they do have to manage a lot of data. So think about a network router, for example. Network routers don't have any persistent storage, but they got a big routing table that they have to manage. But it doesn't need to be persistent. If the router goes down, when it comes back up, it's going to talk to its peers on the network, and it's going to build a new routing table on the fly dynamically. Same sort of situation for the set-top box and the digital television. That set-top box, especially low-end set-top boxes, don't have any persistent storage. Set-top boxes with DVRs do, but we still don't use that persistent storage to store the TV guide. The TV guide is only stored in memory. That's for a couple of reasons. We don't want using the TV guide to interrupt the DVR, and we want the user to have a good experience. When they push a button on the remote control, we want to see something happen on the screen. So it needs to have a peppy response. So you want an in-memory database for that. But if you lose power at your house, of course your set-top box loses power, and that TV guide goes away. So when your power comes back up, you turn on the TV and you go to the TV guide, and it says this information will be available shortly. And that's because it's downloading a new TV guide from the satellite transponder or the cable end-to-end carousel. So there's a whole wealth of different types of applications that can benefit or absolutely require an in-memory database.
Another question that's come in, I'm assuming that this pertains to ExtremeDB. It asks, do we have any classification of tables based on their need for A, frequency of updates, or B, the number of nodes in a distributed system that need to update a given table?
So the answer is twofold. First of all, in an ExtremeDB schema, you can declare individual tables as either being in memory or persistent. And then the second half of that question is really in the context of ExtremeDB cluster, where you can have multiple nodes in a cluster where each node is doing its own updates. And the extent to which we do what the attendee is asked there is that we have a feature where you can define local tables. And these are tables that are, as the name implies, local to that node. So all the reads or all the writes to that node are not automatically replicated to every other node in the cluster. Now, other nodes in the cluster can request the local tables of another node, and a given node can scatter its local table or tables out to other nodes. But that's done on demand whenever the application requests it.
All right, thanks. Another question that's come in is, what happens if the database size exceeds the RAM size?
I can only speak to ExtremeDB, not other in-memory databases. With ExtremeDB, when you create an in-memory database, it's up to you to allocate the memory for that database, either by calling malloc or by passing in arguments that tell ExtremeDB how much shared memory to allocate on your application's behalf. But in either case, it's a size that's determined by the application, not by ExtremeDB. So if you want to have let's say a 100 megabyte in-memory database, then you either allocate 100 megabytes for ExtremeDB, or you tell ExtremeDB to allocate 100 megabytes of shared memory. And if that gets filled up, then ExtremeDB is going to return an error code to the transaction that attempted to overflow that database, and that error code will indicate the database is full and put that transaction into an error state. And it's up to the application to do something about that. Now, what the application does is up to the application to decide. It might go prune the database to make some space available and then retry the transaction, or if it's an acceptable thing to do for this type of application, you can go out and allocate some more memory and extend the size of that in-memory database. Now, what the question might have meant is what I alluded to earlier, is can you create an in-memory database that's larger than the physical RAM size? And again, that answer is yes, but it's not a good idea. So, on a Linux system, you got 2 gigabytes of address space, but if your system physically only has a gigabyte of memory, you really don't want to create an in-memory database larger than that, because you're going to cause the operating system to swap memory pages that actually represent the in-memory database in and out of the swap file, and that's a really bad idea.